Hi everyone, my name is Mary Arnhart, and today I will be looking at a damage plasticity model for human cortical bone. And this is something that I work on in my research, so I wanted to apply this to this course. And I'm looking at the material cortical bone, which is a quasi-brittle material. And so to start out, I will talk about the material, this cortical bone beam, and the setup that we're using to observe the nonlinearities. So we can see here, this is a 3-point bend test, and that is what we're going to be using to look at the nonlinearities in the system, and in this case, specifically looking at damage accumulation. So this is just a standard ASME type of 3-point bend setup, where there's these two supports on the bottom that are fixed, and then these have a span of 16 millimeters, and then we have this human bone beam, and this is cut out of a human femur. This is just for the material properties purposes, but we make this rectangular prism that is out of this bone femur, and it is a 4x4 cross section, and then a length of 24 millimeters. And so there's this force that's applied at the center, and the distance between the bottom fixtures and the load is 8 millimeters. So this is a picture from the SEM of the human cortical bone beam, and this is the 4x4 cross section, and this is at that fracture point. So once this this loads, there's this separation between the compression on the top half, and then there's that tension on the bottom half. And so once this undergoes fracture, you can put this in the SEM, and this is just a way to sort of visualize the nonlinearities in a way that I find useful. And this is where the fracture process zone begins to develop. So this is where, when it undergoes this on this tension side, you can see there's this what's called osteon pullout. And so that's where you see the surface roughness on the tensile side of the beam, and it's up to about 1 millimeter in length into the depth of the tensile side of the beam. And so that's something that's representative of the nonlinearity in the system, and just a visual. The nonlinearity is that there's this linear type of stress distribution, and as we approach this tensile side of the beam where this fracture process zone begins developing, is where this disruption occurs because of the nonlinearities in the system. So this is just really important to look at the mechanical properties of bone so that we can figure out ways to help with fracture occurrences that happen in aging population. So that's really important in the and applications in mechanics can really aid in this crisis of age-related fracture. So that's something that I wanted to look at here, as show some of the literature where there's this experiment, and it's this 3-point bend experiment that's pretty similar to what I'm trying to do in this project, and a good reference for comparison. And something that's really cool that emerges out of this is we can see stress whitening occurring here. And this is where we see, this is indicative of the nonlinearities and this damage accumulation, and we can actually see this in the abacus model, which I'll get to once I get to those results there. And so this red contour line, this is a bovine bone, and this is where this stress distribution is occurring. And so we can see this is Jungmann and others, and there's this force versus displacement curve, and we can see that there's this hybrid between a plasticity and damage model. And we can see plasticity occurring, and then there's this disruption here at this maximum force, and then this damage accumulation begins to occur. And you can see it descend as displacement continues. So here's a couple examples pulled out of the Abacus Theory Manual, which are really good when describing plasticity and damage. And this is a uniaxial compression case, which is similar to what we're doing. And a couple examples to describe this, it's this combination between plasticity and damage that we see here. And so we can see this stress versus strain curve, where the stress initializes, we get this accumulating plastic deformation. And then you reach this ultimate stress, and that's where D equals 0 here. And that's where this initial damage begins. And so in the second graph, this one here, you can see there's this dotted line, And this trend, it would have been assumed to follow this dotted line if it were just plasticity and there's no damage occurring. But because there is damage occurring, as it's a quasi-brittle material, it begins to descend. And so the difference between these two, the dotted line and then this real trend that comes from damage, that's where this accumulation begins to become discernible. And so this is the elastic modulus right here that you can see whenever there is this accumulating plastic deformation. And so this, when damage begins to occur, the stiffness matrix alters and it decreases. And so ultimately the modulus, this slope, it decreases, and overall we can see the trend changing from each point on this curve. And so that's just really important when we look at the stress versus strain, when we look at our abacus model and in the implemented solver. So here in this slide, I'll combine looking at some of the boundary conditions and these equations that we're using, as well as how the abacus model was developed for this simulation. So once again, we have this fixture and this system, and this is just mocked up, the 3-point bend test. And in abacus, the mesh is a global size of 0.5. And these boundary conditions, they're applied where at the support at x equals 0 and x equals L, they are fixed, as well as the fact that they are restriction and rotation at the supports as well. So there's this load that's applied, and the remaining equations are created or developed with this Timoshenko theory. And this is for the equilibrium equations, and we have these reactions as well as balances of the applied moment. So we can look at the constitutive equations, and these are fundamental in the Timoshenko theory and how the stress and strains within the beam are related based on the material properties. And so they play a crucial role when we analyze behavior of the bone beams and calculating the internal forces. They look at deformations when subjected to these external loads, such as force applied at the middle of the beam, and the strong form contains the governing differential equations and the boundary conditions for the constraints. So we can develop strong and weak form, and we can rewrite the governing equations with that in mind. And so whenever we look specifically over the element, we can start to develop the weighted residual and this integral to create the function for the weak and strong form. So when we look at abacus results, we can pull out the stress strain curves and then the load and displacement, which is done here in these abacus results. So we can see here there's this plastic region that begins to develop. It's very high modulus of elasticity, and then there's this plastic region that starts to develop here at the top. And then once damage begins to initialize, you can see that there's this slope and it changes as damage begins to accumulate. The stiffness matrix decreases, and something else that's really interesting that I would like to show is in the abacus model, they have this ability to look at the tensile damage accumulation at increasing time step. And so I want to relate this back into the literature. I'll do that at the end where you can do a comparison. But you can see there's that stress whitening that you can kind of visualize in the experiment as well. So that's pretty cool, and I'll show that at the end, sort of a comparison. So here's the implemented solver results. The implemented solver is a little bit more simplified. It's developed in Python, the Jupyter Notebook, and you can see that the modulus of elasticity is a little different. There's this tiny bit of plasticity that develops, but it's mainly focused on the damage accumulation where the slope changes. And to start to develop this, we have to look at the governing stress-strain relations, and they are scaled by damage elasticity. And so to describe this portion here, we can use the D0 elastic. This is the elastic stiffness of the material and is the degraded elastic stiffness. And then the lowercase d is the scalar stiffness degradation variable. And so we can take that value in the range from 0, so that's undamaged, and then to 1, and that's fully damaged. And so that's the damage associated with failure. The failure of mechanisms of concrete used here, so that's sort of the module that I'm following. It's this concrete with this, it's a quasi-brittle material, and so we're using it to reference and develop these models, and this results in a reduction in the elastic stiffness. So within the context of scalar damage theory, this stiffness degradation is isotropic and characterized by that single variable. The Cauchy stress is related to the effective stress through that scalar degradation relation. So we can ultimately create this comparison done here, but it's important to keep in mind that there's simplifications that are made in the implemented solver case. So this is the literature comparison that I mentioned earlier. So just here I want to compare the Abacus results to the literature mentioned by Jungmann and others, where there's major geometric differences here, but this is trabecular bone, it's spongier, and then just the dimensions are different. But I do want to sort of look at the comparison. You can see the stress whitening, the damage accumulation that's occurring, and also this force versus displacement curve. While it's different in magnitude, the trends are sort of similar here. And yeah, so lastly, I would just like to conclude that this course made it possible to comprehend and quantify and model nonlinearities introduced into the system by damage. And so we can really leverage FEA into understanding materials and understanding the mechanisms of the nonlinearities and investigate and be able to treat and aid in these types of models, looking at these mechanical behaviors. And so, yeah, I just want to thank you all, and yeah.